Okay, Assalamualaikum and very good morning to all of you. So welcome to our lecture session for mechanical vibration subject. Okay, so we're still in the chapter 1, basic of vibration lah. So yesterday class we have covered the basic elements vibration, the stiffness elements, spring element, damper element, and also the mass. So we have go in detail for the stiffness element. Okay, so now we look at the exercise lah, related with the spring elements. Okay, so this is example lah, simple example. How to determine the spring equivalence, the equivalent of the spring, which is if there is a more than one spring attached on the mass lah. So if you have any kind of the spring mass system and a lot of spring attached to the mass, the first thing you have to find that what is the equivalent stiffness for that system lah. Okay, so for this system, first we have to identify the arrangement of the spring is either parallels or series, and so that we can calculate the equivalent stiffness. Okay, so for this one, because there is combination series parallel, so we have to solve part by parts lah. Okay, so we solve for this one lah. Okay, so we take this part. Okay, so this one can consider as a K equivalence 1. Okay, and then this spring as a K equivalence 2. Okay, and then we can take all of this side, okay, as a K equivalence 3. And then this one is a K equivalence 4. Okay, and then the rest is K equivalence. Okay, so we do the first K equivalence, K equivalence 1. So we know that this plane 2K and 3K stiffness. First you have to look the nodes, the node which is the position, the end of the spring. Okay, so this end of the spring and this end of the spring is share the same node. Okay, so meaning that it's parallels. Okay, so parallels you can just sum all the stiffness. So K equivalent 1 here is equivalence to (2K plus 3K). So equivalence to 5K. Okay, and then K equivalence 2 also share the same node. So just consider that the displacement for all the spring is equivalence. Okay, so K equivalence 2 K plus 2K plus 3K to this is a 6K lah. Okay, so K is a constant lah, so which is can be any value. Okay, now we go for the K equivalence tree. Okay, so K equivalence tree is a combination of K equivalent 1, K equivalence 2, and K. Okay, so which is it have they don't share the same node, so mean that the arrangement for these springs you can consider as a series. Okay, so series is to find the K equivalence tree is a 1 over K equivalence tree equal to, okay, so 1 over K equivalent 1, so which is 1 over 5K lah, over 5K, then plus 1 over 6K plus 1 over K. Okay, so this is K equivalent tree lah, and then to solve, I think you can get 30 lah. Okay, so 6 plus 5 plus 30 over 30K. So which is equal to 41 over 30K. Okay, so which is can write as a K equivalence tree is equal to 30 over 40K. Sorry, 30 over 41. Okay, now we go for the other side. Okay, so which is in our right hand side lah. Okay, so this part, so K, 2K, and 3K. So you know that all these spring doesn't share the same node, so meaning that is in the series arrangement lah. So K equivalence 4. So 1 over K equivalent 4 is equal to 1 over K plus 1 over 2K plus 1 over 3K. So which is equal to 6 plus 3 plus 2. Which is this one is 11 over 6K. So which is K equivalence 4 equal to 6 over 11K. Okay, and then the overall K equivalence, so we know that the K equivalence 4 and K equivalence 3. Okay, so what is the arrangement we can consider for the K equivalent 4 and K equivalence 3? Okay, so for this system, okay, so this side and this side, we know that the total allocation for the K equivalence 3 and K equivalence 4 is same, because it's there. Both of the K equivalent is directly contact to the mass, so meaning that the deflection for the K equivalence 3 and K equivalence 4 is depend on the movement of the mass. So for this case, we can consider as a the parallel arrangement. So in overall, the K equivalence equal to K equivalence 3 plus K equivalence 4 lah. Okay, so you can just plus K plus 6 over 11K. Okay, so you can just calculate lah. Okay, so that's all the final answer. So maybe you can just make it in fraction or can make it as decimal places. I don't have calculator right now. Okay, so this one is enough lah to get the answer. Okay, so that is how we find the K equivalence for the system which consisted of more than one spring in the system. Okay. Okay, there is another example. Okay, for this example, so it's a machine of a. Okay, before I forgot, please write your name and your matrix number on the chat box. Okay, for my attendance record. Those thank you for those who already done it. Okay, so now we continue. Another example. Okay, so this is a machine of a mass of 500 kg is mounted on a simply supported steel beam with a length of 2 meters, having a rectangular cross section with the dimension of zero point 0.1 depth and width is 1.2 meter. Okay, and then the yaw modulus for this beam is 2.06 time by 10 power of 11 Newton over meter square. Okay, to reduce the vertical deflection of the beam, a spring of a stiffness K is attached at the midspan, shown in the figure below, and then determines the value of K needed to reduce the deflection of the beam by 25% of the original value, 50% of the original value, and 75%. Okay, so basically there is only a simply supported steel beam lah. Okay, so now you have deflection. Okay, so but first we have to find the original deflection lah. So for this case we have to calculate the stiffness of this beam. Okay, so everything is given, so we just have to use the equation lah. Okay, and now based on the original deflection, we want to reduce the deflection, which is we add another resistance to resistor, which is we add another spring. Okay, we add another spring in the middle of the beam. Okay, so now we have to identify what is to determine the value of K to reduce the deflection based on the requirement in the question 25%, 50%, and 75%. Okay, so for this case, we have to know that this is a simply supported beam. Okay, so simply supported beam. First, we want to calculate the actual deflection lah. Okay, so this one actually when we the stiffness is only related with the hook law lah. Okay, so we know that F is equal to Kx. Okay, so we want to find the X. Okay, so this is we are going to determine. Okay, and then F here is based on the weight of the machine. Okay, so this one is the weight. And then K we can calculate lah. Okay, so K is equal to so this one is simply supported so you can just refer to the equation lah. So K beam lah, KB is equal to 48 E over so this is the general equation for the simply supported beam. If we want to find the stiffness when the load apply at the midpoint lah. Okay, so E is the Young modulus is given, I is polar moment of inertia, so we can calculate lah. Okay, so I is equal to 1 over 12. The base is a 1.3, sorry 1.2 times by the depth is 0.1, then the cubic. Okay, so this we got 1 times by 10 power of minus 5 meter power of 4. So make sure when you do the calculation, all the units should be in SI units. Okay. So now we can calculate the KB lah. Okay, so KB beam lah here. K beam is 48 times by 2.06 10 power of 11 and then times by 4. L is given in the question, so which is 2 meter, 2 power of 3. Okay, so this you should got 1.236 times by 10 power of 8. Okay, so now we go for the first question. First, we want to find the x value lah. Okay. So in this okay, so x is equal to weight over deflection okay lah. Okay, so it's a 500 times by the gravity over K lah. So 1.2 K should be Newton unit, Newton over meter. So roughly x is equal to 4 times by 10 power of minus 5. Okay, so this is the initial deflection lah, the amount of deflection. Okay, so now the question asks to add another spring lah, spring in the middle. Okay, so to ensure that we can reduce the total deflection lah. Okay, so total deflection 25%. Okay, so 25% from the 4, so we reduce 1 times by 10 power of 5 meter, so mean that is the value is 3 lah. Okay, so now we go for the solution for A. So A x new lah, x new is 0.75 lah times by so 4 10 power of minus 5, so which is equivalent to 3 times 10 power of minus 5 meter. Okay, so from that, first we want to know that what is the required stiffness lah, to ensure that the deflection is only 3 times 10 power of minus 5 lah, because the weight is constant lah. Okay, so the K equivalent should be weight over x new lah. Okay, then which is equal to 163 5. So 50. Okay, 10 over meter. Okay, so this is the required K equivalent. So now we look at the arrangement. Okay, so now we add another spring in the middle. So we have to identify either both of the spring in the parallel or series arrangement. Okay, so to identify, first as mentioned before, you have to know that the node. Okay, so the node, which is the deflection of the first spring and second spring, share the same node lah, because it's directly attached, which is direct contact to the mass, which is the deflection of the mass is equivalent for the deflection for the K and then K beam lah. So for this case, we know that the K equivalent should be equal to K beam plus K, so which is the stiffness we want to add lah. So this is the parallel arrangement lah. Okay, so if we want to calculate the K value, so K should be equal to K equivalence minus K beam lah. Okay, so we have already calculate. So which is equal to 4 times 10 power of minus 7 lah. Sorry, 10 power 7 Newton over meter. Okay, so this is the A, and B and C, I think just a repetition lah. Okay, so B, we want to reduce 50%. So just repeat the same procedure, and then the K equivalent should be 2, 4, 5, 5, 0, 10 per meter, and K equal to 1.22 10 over meter. The same goes for the C lah. C, which is 75%. So we want to reduce 75% from the 5 times by 4 times by 10 power of minus 5 meter. Okay, so K equivalence should be equal to 4.5. So K equal to 3.67. Okay, so that's all for this question. So the most important thing that you know that how to assess the arrangement of the spring. Okay, so you know that either is a parallel or series. The basic concept is simple. If both of the spring share the same node, so which is the deflection for both of the spring is equal, and we can assume that we can say that the spring in the parallel lah, the parallel arrangement is the node is not, if both of the spring doesn't share the same node, so mean that is a series. Okay, so that the spring lah. So now we go for the another elements, which is damping elements. Okay, damping is basically used to uh, reduce the vibration lah, to absorb the vibration. Okay, so this element is very important lah, because we know that in the actual system there is damping. So if we know the value of the damping, then we can accurately predict the vibration response lah. So because if there is a presence of damping, the amplitude of vibration will not be constant lah. So there is decay in the amplitude, and if we know the amount of damping, then we can predict the position of the mass lah. To the vibration response means that how the mass is vibrate. Damper is assumed to have neither mass or elastic lah. So which is this one is relative to the velocity. Damping force exists only if there is a relative velocity between two end of the damper lah. So which is uh, if there is a relative velocity lah. So if the velocity change, so meaning there is no velocity. But if both of the end damper have a relative velocity, so meaning that we create the damping force lah. So for the normal application, we use a dashboard lah, dashboard or damper to represent the damping element or to represent the damper. Only we use the viscous damper lah. Actually, the damper is already there, but for example, the damping in the materials damping is there for the stiffness, for the spring itself, and the structure body, but that value is not easy to be determined. Okay, you need a very complex measurement method lah. So that's why uh, to create the damper, the damping elements, to control the damping, we use a dashboard lah, as for to as something that to absorb the vibration lah. So dashboard is easier to control lah, because we can set the value for the damping coefficient. And then this one is the symbols lah. So basically damping force is relative to the velocity lah. So v is velocity here, or we use as a x dot, which is we differentiate the displacement. Okay, so c dt of dx over dt lah. Okay, so which is damping force is linear to the velocity. When the velocity increase, the force produced by that damper also increase, the resistance lah, the resistance also increase. Okay, normally the damping is based on the we use the viscous damping. The dashboard is depend on the properties of the fluid used to develop the damper lah. So This one we not detail out lah. Just you have to know that it's based on the shear stress that which is the friction lah between the feet and the inside the dashboard lah. Okay. So which is the shear is a relative to the mu is the the properties of the liquid lah. Then the velocity lah. And then this is the force and how we got the relationship lah. F equal to CV. And then C is the damping constant lah. Okay. So don't worry about this equation. Normally for the damping constant, it's just a single value lah. So the value is there. You don't have to calculate based on this equation lah. Okay, so that's the concept lah. How we get the C value lah. Okay, so this is the type of damping. Okay, so there is a structural damping. So this one is which is as mentioned, inside all the material itself have their own damping lah, damping value. It's due to the friction of the molecule inside that material. So if there is a deflection, then the interactions between molecule can create the damping. So that's why all the structure have their own damping. So for example, if you have cantilever beam, you put mass, you give initial displacement, and then the mass is vibrate. So, but after certain period, it stop. Okay, so stop meaning that there is something the external force that forcing it to stop lah. So because if you consider free vibration, spring mass system without damper, if you give any disturbance, it will keep oscillate without any decrement in terms of amplitude lah. So but you know that for the actual structure, if you replicate that situations after certain periods, the mass will stop. Okay, so why it stop is because the presence of the damping elements lah. So damping elements mostly is dominated by the structure damping inside the cantilever beam itself. Okay, so that damping we create the resistance lah. So the damping force to reduce the vibration level lah. So that's why you can see that if you make it the vibration for that kind of system, the amplitude will decay by the times when the time increase lah. So after that we stop lah. So that's due to the damping. Okay, and then actually structure damping is not easy to determine, but is you can still get this value based on the model testing lah. So which is you give initial disturbance and then you can predict the decay of amplitude lah. From that we can estimate. Okay, but actually for that kind of situation, there is a lot more other damping that contribute to that. That's kind of vibration lah. For example, the air friction itself also can create the damping lah. Okay, so now we move for the viscous damping. Okay, so viscous damping is mostly used as a damping coefficient to control the vibrations. Okay, so because the material you cannot control. The material, if you create that geometry, is structure damping is depend on the geometry and the properties, the type of materials lah. So you cannot control. If you want to the damping, you cannot control the geometry. Is not easy lah. So that's why to control the vibrations, we use the viscous damping. Okay, so you can you design the damping, the damper with your desired value of damping coefficients. So it's depend on uh, this relationship lah. So the previous one, so this one. Okay, so this one is very important because uh, the damping play the big roles to avoid the uh, especially in automotive lah. Automotive we talk about the car. Okay, if you drive a car, you hit the bump, and then uh, the car there's bumping, right? Uh, the damping is play the rules how we want to reduce the motion of the car lah in the vertical. So because when you hit the bump, the car move, and then after that, if you don't have a sufficient damping amount, it will keep vibrating. Okay, so that's why you have to consider that the weight of the car, the stiffness of the spring. Okay, and then from that you can calculate, you can estimate the requirement of damping value to ensure that it's enough to ensure that the car doesn't vibrate, doesn't move in the vertical direction after it hits the bump lah. So it's related to the damping criticals value. Okay, so for example, you require 2000 Newton seconds per meter, then you have to design the dashboard. At the dashboard, your absorber should have damping coefficient is equivalent to the 2000 or more lah. So more is because uh, the larger damping coefficient value, the greater value for the C coefficient is better, but it's not easy lah to fit that dashboard with very high coefficient. Okay, so that's why we have to, in economical point of view, we have to make sure that it's enough lah for a certain kind of uh, car lah. Okay, and the most important thing for if you go for the more luxurious car, they separated the system, which is its body is other mass, and then the tire is other system lah. So which is only tire if movement, the movement is only on the tire, and then the force from the deflection of the tire doesn't transmitted to the car body is due to the damping lah. So because it's very absorbed, and then the end of the absorber have a very minimum deflection lah. So from that, the car body doesn't have just receive the minimum motion in the vertical direction lah. So that's why viscous damping is mostly used lah to control the vibration. And same goes for the machinery. Okay, so if you found that your machinery have a high vibration issue, and then um, you don't know how to solve it, which is already control the speed, control the structure, and it still have the high vibrations. So for that kind of solutions, you can add another damper lah. So add another damper, or we call as a isolator lah, isolator with a certain amount of damper to absorb the vibration from that. Because sometimes same goes for your engine, the mounting of the engine, something like that. So ensure that the vibration for the engine doesn't transmit it to the car body, and same goes for the machinery industry. Okay, so when the machinery is in operating, they produce the high force, okay, high forces, which is can create the high vibration. So even the machine have high vibration, sometimes the structure that support that machine cannot sustain that kind of force. So that's why for the certain solution, you can add damper at the support of the machine to ensure that the vibration from the machine doesn't transmit, which is the force transmitted to the structure is very minimal, which is the vibration to the structure is less than maximum allowable limits of the vibration. And then the last one is column damping. So this one is device friction. Okay, so which is the frictions between two object lah. So it's depend on the the surface roughness lah. Okay, so uh, you can calculate based on the F equal to mu n lah. So n is a nominal force. I think you have studied in the static. So that's kind of the friction damping, dual friction column damping lah, because it's a column damping. Okay, so so I think that's all for the damping lah. So you have to know that how we use the damping to control the vibration lah. So mostly damping is used to to control the level of vibrations. Okay, in operating, if we add the high damping, and then we can reduce the amplitude of vibration. Okay, so now we go for the classification of vibrations. Okay, so first we can classify by two lah, free vibration and forced vibration. Okay, so if you have a mass, okay, and then for the free vibrations, the mass is vibrate just due to the initial disturbance. Okay, so system vibrate by its with the initial disturbance applied to the system. Okay, so for example, you have spring mass system. Okay, so you press the mass and then you release, then the mass will oscillate. Okay, so this that kind of motion we call as a free vibration, because there is no external force induced to the system. So this one we can consider as a free vibrations. Because it moves just based on the initial condition applied lah. Okay, so if we keep oscillate lah, so it's depend lah. If there is no damping, if we keep oscillation until you stop it, and if there is a damping, and then after certain period the amplitude will decay, and then after certain period it will stop lah. So that's free vibration. Okay, so what you have to know that the free vibrations, the amplitude of the vibrations is depend on the initial condition. Okay, so for example, you have spring mass system. Spring mass system. Now that system in the equilibrium position, static equilibrium position, and then you press, and then it's vibrate. Okay, so the amplitude of vibration actually is depend on how much you deflect that mass. So if you deflect for the 10 mm, for example, and then it will vibrate, and then the vibration should be lower than if you press at the 50 mm, for example. If you press 50 mm, and then the amplitude of the vibrations we increase. So the amplitude, which is the deflection, the deflection of the amplitude of vibration, it goes up and down. So which is can goes at the higher amplitude if you have give the higher value of initial conditions. So that's the concept of free vibration. And in vibration, we know that there is amplitude and there is a frequency. Okay, so amplitude, um, how much it's deflect. Okay, so which is the motion lah. So which is from the equilibrium to the maximum point. So that's the amplitude of vibration. And apart from that, it also have the frequency of oscillation. Okay, so frequency of oscillation is actually is referred to the how fast uh, the 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 mass vibrate for the one complete oscillation lah. Okay, for example, 1 hertz within 1 second goes it goes up, down, back to the actual position. So that is a one complete oscillation lah. So that's refer to the frequency lah. So 1 hertz. 10 hertz within 1 second it move 10 times. So this is how fast it move lah. So that is the frequency, which is how fast it's move. The amplitude is the range of motion. Okay, so the amplitude is depend on the initial condition. Okay, so you give higher initial condition, you got a higher amplitude. But for the frequency is depend on the properties, the variables, so the parameters for that system is depend on the mass and spring. So what is the mass value and what is the spring stiffness. Okay, so which is we call as a natural frequency lah. So free vibration, you give initial condition and then we vibrate. The frequency of oscillation is equivalent to its natural frequency. So that's one of the method to know that the natural frequency of the system lah, or the single degree of freedom. Okay, so free vibrations, the amplitude is depend on the amount of the amount of initial condition, and then the frequency is depend on the natural frequency. Okay, so it will vibrate at their own natural frequency. So that is a free vibration lah. And then we go for the forced vibration. Okay, so forced vibrations, the condition that when there is external force induced to the system. Okay, so that's commonly happen in the industry lah, industry application, when there is a machinery in the running condition. Okay, so which is any rotating machinery can produce the harmonics excitation. Okay, so the rotating unbalance. Okay, so if there is rotating equipments, the unbalance can produce the force, unbalance force. And even every components, the gear, the bearing. Okay, so all of that we induce the we call as a harmonics force. Because you are mechanical engineer, you deal with a lot of this kind of machinery lah. You have a rotating machinery, either it's a centrifugal force or it can be the reciprocating. Okay, so the engines also can produce the harmonic excitation, the car engines, for example. So this one is we call the force vibration, because when we start the machine running and it's vibrate. So that the vibration is due by that machinery is considered as a force vibration, which is force is come from the machine itself. Okay, so this one we call as a force vibration, because if we run the machine, it's vibrate. We stop the machine, it doesn't vibrate. So that is the force vibration. It's due the force induced by the machine. Okay, so the difference between free vibration and force vibration. For the force vibrations, the amplitude is depend on the amount of force induced by force vibration lah. And apart from that, it also relates with the resonance phenomena. Okay, so the amplitude of vibration is depend on the amount of force induced by machine. So the higher force induced by the machine, it produce the higher vibration. Okay, so that's why if the machine in the faulty condition, you may find that have the higher vibration lah, because the faulty machinery can produce the higher force to the system lah. Higher force produce higher vibration. Same goes for your car engine. If there is something defect of the car engines, the car will vibrate the higher vibration. So that's why you feel that uh, your car will vibrate higher lah. So that's due to the faulty machinery lah. So faulty machinery can induce the high vibration, but it's not only the reasons lah. The high vibration sometimes is due to the resonance phenomena. Okay, so if your excitation frequency, so which is the speed of operating, your your RPM of the car engines is close to the one of its natural frequency, and then it can also produce the high vibration. So that the force of vibration. So which is the amplitude is depend on the amount of force induced and also the closeness to its natural frequency. So that's the factor that contribute to the higher vibration. Okay, so it's related to resonance. So resonance phenomena we can define as when the excitation frequency is coincides with one of the natural frequency of the system, and then can create the high vibration phenomena. So that's phenomena we call as a resonance. So resonance is something that we don't want to happen. So for the resonance, so you have to tackle the resonance issue lah. So to ensure that your running speed doesn't coincide with the natural frequency. Okay, so difference between free vibration and forced vibration. Free vibration, the frequency is depend on its natural frequency. Okay, so if natural frequency is 10, you give the initial disturbance and then it will vibrate at 10 hertz, the 10 hertz lah. So that's the normal. No matter how much you press, the frequency is still same. Okay, so the time taken to complete one oscillation is still same. But for the forced vibrations, is the frequency of the vibration is depend on the frequency of excitation. Okay, so for example, if you run the machine, okay, the motor, okay, you run the motor at 50 hertz, and then the system will vibrate at 50 hertz. Okay, so it's depend on the operating speed lah. So that's the difference between forced and free vibration. Free vibration, the frequency is dependent to the mass and spin, which is really the parameters to calculate the natural frequency. Okay, so basically the natural frequency omega is equivalent to square root k over m lah. So another signal, another k, and then you can predict. Okay. But force vibration is depend on the speed of excitation. So it's running speed lah, to make it easy. You run the motor 10 hertz, you got the response 10 hertz. But the amplitude is depend. It's depend on the force induced. Higher force, higher vibration. That's the normal relationship lah. And then apart from that, it also relates with the resonance. You run close to the resonant frequency, you got the higher vibration. It's coincide, then there is a resonance. So this is a free and forced vibration, and then there is also undamped and damped vibrations. Okay, so undamped vibration, so meaning that the system only consists of a spring mass system lah, no damper. Okay, so under free vibrations for the undamped system, it will move with the same amplitude lah. So for example, if this mass, okay, we move, you give initial disturbance, spring mass, and then it will oscillate. And it will keep oscillating with the same amplitude, okay, so without any constant amplitude lah. So oscillate with constant amplitude. So that's the free vibration lah. So no amplitude decay and energy loss. That's for the free vibration lah. And then there is a damped vibrations. So damped vibration, which is there is a loss of energy due to friction or other resistance. So which is the presence of the damping elements. And then for this kind of vibration, the amplitude will decrease. So the decay of the amplitude with time. Okay, so for example, this damp system, you press and then you release, so it's vibrate. Okay, okay, after certain period and then it stop. So that's kind of the damp vibrations. Okay, so which is if there is a damping, then it will stop lah. So it's depend on the amount of damping lah, damping coefficients. Okay, so higher value of damping, you have less oscillation lah. So that's classification lah. So basically in this topic, this subject, there is a two chapter, two parts, CO1, CO2. CO1 is covered for the 1 degree of freedom. So there is a 4 cluster of vibration lah. So that's why you have to identify which kind of vibration you face, especially to answer the question lah. Okay, so it's the damp, undamped, free, or force lah. So from that, once you identify that, then you can go for the solution lah. Okay, so now this is the vibration analysis procedure. Okay, so this is the step by step to solve the vibrations problems. Okay, so first, there is a system of intervals. Okay, so what kind of vibration you want to study? Okay, so you want to study a spring mass system. Okay, and then you model the system. Okay, so you model the system based on the elements lah. So you have to know what is the equivalent mass for that system, what is the equivalent stiffness for that system, what is the equivalent damping for that system. Okay, so once you construct the model and you calculate all the equivalence parameters for that system, and then you start governing the equation. So governing equation is depend on the motion you are interested. If you deal with the translation motion, then you have to consider that the the total force applied to the system lah. So the total force should be equal to 0 under dynamic equilibrium. Okay, so governing equation, so total force, and then you identify all the forces. Force comes from the spring, force comes from the damper, force comes from the mass or inertia. So based on the this relationship lah. So this one, F equal to ma, or for the rotational, we consider the moment lah. Okay. And then solve analytical numerical computation is depend lah. So solve mean that you find that the motion lah, once to study the motion. So for the simple system, single degree, 2 degree, 3 degree of freedom, you can use the manual calculation lah. But if you deal for the more complex system, then you can go for the numerical solution or computation analysis using FEA software. Then interpret the result and refine as necessary. So that's the way how to solve the vibration. Okay, so this is the first step. Mathematical modeling. So what you have to include in model. So for example, automotive moving on uneven road surface. So we model the vehicle as a single, two, or multi-degree of freedom lah. So it depends. You have the system of interest. You want to model is a single degree, 2 degree, or multi-degree lah. It depends. Then how model to the road lah. So model the roads. Roads actually is we can consider as a the force vibration lah. So because when you move on the uneven road surface, okay, so the road profile we induce the force lah. We consider based on the road profile is equivalent to the force lah. Force deflection force. Then the suspension system, okay, so the tire, so the suspension system is related to the stiffness, the damping for that system lah, and then the tire itself, the tire can be considered also part of the stiffness lah. And then derive the governing equations. So physical law we use, okay, so total force or total moments lah. And then solution the governing equation. Okay, can we solve numerical in the closed form, approximate, numerical lah. So the single degree of freedom is still simple. Can solve as a simple by manual calculation lah. So we discuss in the next chapter. Approximate, okay, so approximate and numerical lah. Numerical normally we use a computational software or programming lah. Then interpret the result lah. Information. What information does the analysis in our model provided? Okay, the information lah, which is all the parameters and consistent experiment result. Okay. So basically, if you're going to develop numerical solutions, the most important thing that you have to compare with the experimental data lah. Ensure that the model you develop is equivalent to the actual model. Okay. Especially when you deal with the FEA, finite element analysis. Okay, so you the most important thing, you must develop the equivalence CAD model. Equivalence CAD model. Okay, and then you have to use you must input the correct materials properties, and then the boundary conditions, either is equivalent, because sometimes you use a fixed boundary condition and actual is not fixed. There is still motion lah, so it's not totally fixed. So that's why you have to do the modification. Okay, once you run the software simulation and then you have the equivalence with the actual measurements, and then you can consider that your model is good and equivalent or identical to the actual system lah. So from that, normally for the modification structure, they just do in the CAD model lah, to reduce the time and to get the more accurate result. So you do the modification on the CAD model. For example, you want to stiffen the structure to change its natural frequency, then you can add another a beam, for example, to stiffen the structure, and then you can see what happened after that. What is the value natural frequency when you put that kind of additional components. So that's normally used for the FEA software. So this one to predict future behavior. Or design a better system lah. So for example, you find there is a resonance at 10 Hz. So now you want to change natural frequency of the system to keep it away from 10 Hz. your target to move is more than 15, and then you stiffen the structure. You cannot do to the actual structure, because to modify the actual structure is require a lot of cost lah. You cannot just try and error. Okay, so that's why try and error, you do the try and error on the software. Okay, so, computational simulation. Okay, so you stiffen the structure and then you simulate. Now after you add a new structure, you change the structure, and then what happened to natural frequency, the value for the natural frequency. Now you found that the natural frequency goes to 20, so this one is good lah. So mean that you can apply your solution to the actual structure, then uh, you can do lah. So in the actual structure. So that's commonly how the linkage between the computation simulation and measurements lah to solve the vibration. Okay, so this is example lah for the forming process lah. Okay, so there's the frame, anvil, elastic pad, foundation block. So there will be vibration on the vertical motion. So it's depend. If you want to study the whole system, can model as a single degree of freedom. Okay, so which is this part, the foundation block lah, the vibration of the foundation block and everything. Okay, and then for this you can model anvil and foundation block as one unit lah. So which is we just only want to consider the motion of the whole structure body. And then for this case, the value of damping and stiffness, you must consider is the soil itself lah, the soil damping and the soil stiffness. The tip here is we induce the force lah, okay, the impact force, which is depend on the velocity lah, the velocity of this based on the kinematic analysis lah. So this one for the simple lah. If you look at for the simple solution, you only interested about the whole body motion, then you can just model something like this lah. If you want to go for the more complex, you are interested to study about the motion of the anvil components and also the foundation block, so you want to separate, and then you can model as a 2 degree of freedom lah. Okay, so the anvil as a one body, which is a motion for the anvil, consider for the x1, and then foundation block motion you can consider x2 lah. So both of the body have their own motion, so you can separate by 2 lah. So by this model, if you know all the parameters, then you can estimate the motion of x1 and x2 lah. So that's we call as a solution. This one we only consider the motion of the whole body, which is x1 lah. Okay, so this one another model for the motorcycle. So you want to investigate the vibration in the vertical direction. Consider the elasticity of the tire, elasticity and damping of the strut, which is absorber, mass of the wheel and elasticity. So this is how we model lah. Okay, the simplest model is a single degree of freedom, the equivalent mass, the K equivalence, the damping equivalence. So here the equivalent of the stiffness, we consider that the stiffness of the tire, the strut, and then the rider itself. And then the equivalent of the damping, the strut and the rider. And the equivalent mass, the whole mass include. Okay, so which is wheel, body, and rider. Okay, then this one, we just consider that the motion of the one body. So one body, we can consider the whole motion. So that's if we only want to study that kind of motion, then it's okay, just consider like this model. Okay, so it's enough and it's easier to solve. Okay, but if you are interested to study about the motion of the motorcycle body and also the tire, you want to look at what is the motion of the tire and what is the motion of the body. So you can model like this. Okay, so model like this is this equation, and then if there is a motion, then you can create the equation of motion from that. Okay, so if move to the upward directions, for example, and then what direction for this stiffness, okay, in the tension or compression, the direction of the force due to the stiffness, the direction of the force due to the damping, and then the inertial force. Okay, so inertial equals the opposite. So that's how we model the system lah. From that we can find the motion for this body, the motion of this body, the motion of this body. So we can get the three solution solution for each body. Also this kind of the ni lah. So if you're interested about the body and the tire, we consider have the same movement. Can model like this. Okay, and then this one is we want to refine, to go in more details. So which is we are interested to study the motion of the rider also. Okay, so from that we can split by this. So if you are model like this, the final solution you will get four solution, which is the motion of each tire, and then the motion of the motorcycle body, and then the motion of the rider body lah. So normally for this kind of study, if you are interested about the comfort lah, the comfort study. So which is you look at for the comfort for the driver. So you have to study the motion of the driver. Okay, so that's okay. So about the solution for the vibration system, it's about the system input outputs. Okay, so it's very simple. That's the general solution. Actually, it's not apply for the mechanical vibration only. All the subject can relate with the system lah. Okay, so input output and then the system properties itself lah. How the system property produce input output. Okay, so input which is how you excite the system. Okay, if you give the initial conditions, so then it will vibrate. Vibrate is the output is oscillation. How is vibrate lah? So which is the motion of the object after you give the input, and then how the input we add is depend on the system itself. Okay, so if the system is a spring mass system, doesn't have damping, so it vibrate without any with a constant amplitude. Okay, so that's initial condition. If there is damping, then the response it goes to the decay lah. So that's the system. Then how much you model lah? Single, 2 degree millimole, damp, linear, deterministic, random, continuous, discrete lah. Okay, so if you excite the system with harmonics, harmonic is force the force vibration, and then it's depend on the system. What is the value for the stiffness? What is the value for the mass? It's very important lah. So because if we relate with the natural frequency, and then if you excite the harmonics, what is the speed? The omega here. Okay, so if the omega is close natural frequency, then the outputs will have higher vibration. And then the frequency is depend on the excitation frequency. So that's the relationship lah. Input is the way you induce the periodic. So periodic, which is can refer to the periodic type of response in the previous chapter. In general, there is step, ramp, parabolic. That's why it's the type of excitation lah. But normally for this study, we only focus on the initial condition and then the harmonic excitation lah. And then we see the output. Okay, the output is depend on the system itself. So this is the map lah. The map for the single degree of freedom lah. So I can split by two, free and force vibration. Okay, so if free vibration, if no damping, and then the vibration is is vibrate at their own natural frequency. Okay, if there is a damping, okay, so at the column damping, viscous, okay, and then it's depend on the amount of damping lah. So if less damping, this is under dam lah. So under dam, it still vibrate, but the amplitude will decay after that lah. And then the frequency oscillation is omega d lah. Omega d is damping frequency. It's should be slightly less than omega n lah. And then there is exponential decay. Okay. Based on log document. And if the damping is higher than critical damping, meaning that there is no oscillation for the free vibration. So which is for if you first the system with high damping, you press and then just back to the actual position and the equilibrium position. Okay, so there is no oscillation. So that's how the damping plays the role for the first free vibration. And then same goes for the critically damped overdamped and critically damped, which is there is no oscillation after you give the initial disturbance. So that's the free vibration okay, and then we go for the forced vibration. Okay, so for this subject, I think we more focus on the harmonics. So harmonics excitation if no damping, and then it's depend on the excitation speed excitation speed, and also the force induced higher force, higher vibration. That's all. And then if there is damping, okay, how normally we go for the viscous damping Okay, so if there is damping, how much damping because the higher damping can reduce the vibration response. I think that's all for this topic. Okay, so this basically is a summarize all the what you will learn in the single degree of freedom okay, in the subject. So next we go in details. Okay, so next we go for the free vibrations, undamped one topic, free vibration damp one topic, and then forced vibration damp and undamped and forced vibration damp so next we go in detail to next week. We start to do the calculation or how we model and how we do the solution so not just basically the theoretical it's a general solution so now next you will study about free vibrations, no damping. Okay, so what is the response, which is the x the x equal to a sine omega n plus omega nt so what is the amplitude and what is the the natural frequency and so on. Okay. And next we go for the free vibration damping, and then we go the forced vibration, harmonics, no damping and damping Okay, so that's all for this subject. Okay, so any question before we finish our lecture?
No, doctor.
Okay, so no question.